Hello, dear listeners, and welcome to a new episode of our Letter to Vox podcast. Today, we are undertaking a deep dive into a foundational text that really, it didn't just study science. It fundamentally changed how we think about what science is.
We are, yeah. We're dissecting Thomas S Kuhn's 1962 work, The Structure of Scientific Revolutions. And Kuhn's big argument, the one that really shook things up, was that our traditional view of science, as this steady, cumulative march toward truth, is basically a historical illusion.
Right. It's not just adding bricks to a wall.
Not at all. He argued knowledge advances through these really radical, sometimes violent conceptual breaks. So we're looking at a story of destruction and rebirth, not just a slow buildup of facts.
And I think that's what makes it so electric. Even all these decades later, we all kind of grow up learning science as this neat timeline of great discoveries, one after another.
The textbook version.
Exactly. But Kuhn comes along and suggests the breaks are so total that after a revolution, scientists are looking at the exact same world, but seeing entirely different things. Before we jump into his whole framework, though, let's look at how Thomas Kuhn himself got there, because his own career is kind of a perfect example of his thesis.
It absolutely is. I mean, Kuhn, who we'll call TSK from here on, he started his academic life deeply committed to that traditional view. He was a theoretical physics graduate student, just about finishing his dissertation. So he was completely steeped in the rigor and, the apparent stability of 20th century physics.
As he was a practitioner, he was inside the successful paradigm of his day.
He was. His whole world was one of fixed laws and steady progress. And then something completely unexpected happened. He got involved in this experimental college course at Harvard.
Oh, what was that?
It was designed to teach physical science to non-scientists. And to do it well, he had to immerse himself in the history of science. He started reading all these older, seemingly wrong theories from people like Aristotle.
So he's a physicist forced to read ancient history. And just reading these discarded ideas, it causes a personal crisis for him.
A massive intellectual shock, yeah. He talks about realizing that those older ideas, when you look at them from their own time period, they weren't just bad science or a bunch of mistakes waiting for Newton to come along and fix them.
They were coherent.
Perfectly coherent. They were fully functional intellectual worlds. And this exposure it radically undermined his whole conception of what science was and why it was so successful. He assumed science progressed by adding things up. History showed him it actually progressed by replacing things entirely.
That is such a profound shift. And it leads him to completely abandon physics for the history of science, and then eventually he circles back to philosophy.
He does, and this essay, The Structure of Scientific Revolutions, which he'd been thinking about for almost 15 years before it was published, this is the first full public report on that entire intellectual journey. It's like he published his own revolution.
And the mission of the book is to lay out this new image of science.
Exactly. TSK was really influenced by these modern historical approaches, particularly the work of a historian named Alexandre Koyré, who basically said, we have to stop reading history backwards.
What does that mean, reading it backwards?
It means we have to study out-of-date science from its own viewpoint. We need to give those older opinions the maximum internal coherence we can. See how they fit nature from their perspective, not ours.
And when you do that, the whole idea of science as a simple accumulation just falls apart. You're not looking at a straight line to us. You're looking at these other equally viable structures of thought that just stop being useful.
It forces you to ask, okay, if those old views were coherent and successful in their own right, then how did we get from there to here? And the answer, for TSK, is his most famous concept, the paradigm.
Right. And we should probably define that. What is a paradigm?
For now, let's just say a paradigm is a major scientific achievement that provides a model problems, model solutions for a whole community of practitioners. It's the bedrock certainty that lets them get on with their research.
Okay, so let's unpack the road to that paradigm, what he calls the pre-paradigm state, the route to normal science.
This period, before a mature science forms, is it's characterized by this intense but often really unproductive chaos. In any new field, the raw data, the observations, they're just not enough on their own to get everyone to agree on one single body of belief.
Wait, why not? I mean, if you just gather enough facts, shouldn't a consensus just emerge?
You'd think so, but TSK argues no. He says there's always this apparently arbitrary element, personal preference, metaphysical beliefs, historical accident, that's a key ingredient in whatever belief finally wins out. Without a shared framework to organize it, nature is just too rich. There are too many possible interpretations.
And his big example of this is physical optics before Newton.
Right.
It's a perfect illustration of this chaos.
It's the classic case. Before Newton, there was no single accepted view on what light was. What you had instead was a state of perpetual theoretical warfare between different schools of thought.
And these weren't small disagreements. We're talking about radically incompatible worldviews.
Totally. I mean, think about the conflict. You had the Epicurean school. They thought light was made of tiny particles shooting out from objects.
Corpuscular theory.
Right. Then you had the Aristotelians, who saw light as a sort of modification of the stuff between the object and your eye.
And then the Platonists were even weirder.
They were. The Platonic tradition said light was an interaction between that medium and something coming out of the eye itself.
Wow. So you have light as objects, light as a process, and light as a projection from the viewer. How does any unified science come out of that?
It couldn't. Because there was no common paradigm, every single person writing about optics felt they had to rebuild the entire field from scratch, from first principles.
So every paper is half philosophy, half science.
Pretty much. You had to spend half your time arguing why the other schools were wrong before you could even get to your own new observation. And TSK concludes that the result of all that activity, no matter how smart the individuals were, was something less than science. It just lacked the coherence to move forward quickly.
So a field only becomes mature when it stops arguing about the foundations and starts actually building on them.
Yes. And that divergence finally disappears when one of these competing schools manages a big triumph. It provides a set of achievements and beliefs that becomes the first nearly uniformly accepted paradigm. And this is where that arbitrary element really comes into play.
The arbitrary element sort of tells them where to look, like a flashlight. And the research into electricity before Benjamin Franklin is the perfect example of this.
It is. In the first half of the 18th century, there were tons of ideas about electricity. Some people focused on static, others on attraction. But the group that leaned into the idea of electricity as a material fluid, they started to focus only on certain facts.
They filtered the evidence through their pet theory.
Exactly. And that belief that electricity was a fluid you could move around and capture, that led them to try and bottle it. This focused idea directly resulted in the invention of the Leyden jar, a device that could store huge amounts of electrical charge.
Once you have the Leyden jar, you suddenly have powerful experimental proof for the fluid theory, which then helps that theory become the dominant paradigm for electricity.
It's a classic self-reinforcing loop. The belief, which TSK says had to be externally supplied because the facts alone weren't enough, drove the invention. The invention then provided the key achievement that let people like Franklin finally push the field forward.
And the chaos just vanishes.
It does. For electricity, it happened pretty fast. Between 1740 and 1780, practitioners could finally take the foundations for granted and get on with solving specialized recondite problems. This is the birth of what Kuhn calls normal science.
Okay, so normal science. This is the practice that operates under that universally accepted paradigm. It's got a stable foundation.
Exactly. That achievement provides the model problems and solutions for the whole community.
And you mentioned that the key feature of normal science isn't discovery, it's puzzle solving. That feels like a really radical idea. It kind of goes against the whole hero scientist narrative.
It is, and it's meant to be. The goal of normal science is emphatically not to produce major new things. That would mean the paradigm is flawed. The goal is to solve specific problems, puzzles, under a very strict set of constraints. It's a test of the practitioner's ingenuity.
It's more like being a master craftsman than an explorer. The analogy to a jigsaw puzzle or a crossword is just perfect.
It's explicit in the text. A puzzle has rules, right? You know a jigsaw puzzle can be solved. You have all the pieces. They have to fit together. You can't force them.
And if you can't solve it, the problem is with you, not the puzzle.
Precisely. The normal scientist works with the absolute conviction that the paradigm has all the tools needed to solve the problem. The failure is a personal one, not a failure of the theory.
So the motivation isn't always about the importance of the result, but about the challenge itself. The conviction that you can solve it.
That's a crucial distinction he makes. TSK notes that, say, curing cancer is an extraordinary problem. It might require changing the rules, but determining the precise half-life of an isotope or calculating an asteroid's orbit, those are normal science puzzles. They're vital, but the framework is completely set.
And this constrained activity is mostly about what he calls articulating the paradigm, just making the accepted theory fit nature a little bit better. What does that actually look like in practice?
Well, most normal research falls into a couple of main categories. One is determining universal constants, and the other is figuring out quantitative laws.
Let's talk about constants first. It seems straightforward, just measure things really, really well.
Yeah.
But you're saying even that depends on the paradigm.
It is entirely paradigm dependent. I mean, think about the universal gravitational constant. Big G Newton's Principia established that this constant existed, that the force between two masses would be the same everywhere. But for his main problem, calculating planetary orbits, he could just work with ratios. He didn't actually need to know the number.
So the paradigm defined the problem, but the puzzle of finding the exact number just had to wait.
Exactly. For almost a century after the Principia, nobody even bothered to build an experiment to find G. Then, in the 1790s, Henry Cavendish does his famous experiment with the torsion balance. It was a perfect piece of normal science done a century late because the Newtonian paradigm had defined this constant as a crucial but missing piece of the puzzle.
So even just getting more precise is about fleshing out the existing rules, not challenging them. What about quantitative laws, like Boyle's law or Coulomb's law? We're usually taught that scientists just observe, measure, and then the law just sort of pops out of the data.
And TSK's historical work just blows that idea up. He shows that the theoretical commitment almost always comes before you can even collect the right facts. Take Boyle's law, pressure and volume of a gas. Boyle's experiments weren't even conceivable until people had accepted the idea of air as an elastic fluid. That's a theoretical construct.
The more striking example, though, is Coulomb and the inverse square law for electricity.
Oh, for sure. For Coulomb to get his results, he had to build this incredibly delicate apparatus, a torsion balance, that was designed based on the very theory he was trying to prove.
What do you mean?
He had to assume that electric particles interact at a distance according to an inverse square law first, in order to design an instrument that could then measure it and confirm the relationship. The theory was literally built into the tool.
Wow. So the theory creates the instrument that measures the facts that validate the theory? That is a completely different picture of how science works.
It shows that fact collection in normal science is highly restrictive. It's not just open-ended observation. And this is perfectly illustrated by the giant paradigm of Newtonian dynamics.
The Principia set the stage for centuries of research. It was so successful. But even Newton had to make approximations, right? He left gaps for other people to fill in.
He absolutely did. I mean, when he was calculating planetary orbits, he had to pretend that the only gravity that mattered was between a single planet and the sun. He ignored all the other planets pulling on each other.
Which left these fascinating puzzles for the next generation.
Exactly. The brilliant work of mathematicians like Euler, Lagrange, Laplace, and Gauss for the next 100+ years was largely dedicated to solving these application problems. Things like fixing the long-standing discrepancy in the moon's motion, or figuring out if the solar system was stable over time.
So their groundbreaking work wasn't about finding a new theory of gravity. It was about making Newton's theory fit the observations perfectly. They were master articulators.
They were puzzle solvers of the highest order. And this highlights how normal science, by being so focused, establishes this dense network of commitments, conceptual, theoretical, instrumental, that defines a field. That network is what gives it stability.
But that stability is also what sets the stage for its own collapse. Because that network of commitments, it creates blind spots. It literally stops scientists from seeing things they don't expect.
The restrictions are both the source of its productivity and the source of anomaly. TSK has these incredible examples of how established methods actively delayed discovery.
Okay, let's start with Joseph Priestley and the discovery of oxygen, or the delayed discovery.
Right. Priestley was a chemist working within the phlogiston theory, and he had a very specific standard test for gases, mix them with nitric oxide. This test worked great for all the known gases. But the problem was, his commitment to that procedure was also a commitment to the idea that no gases existed that behaved differently.
So his own ritual was blinding him.
Completely. When he first isolated what we now call oxygen, he ran his standard test. The result was super weird, but instead of questioning his categories, he just called the gas dephlogisticated air. Air was something removed, because his paradigm had no room for a new element like this.
He had the revolutionary substance right there in his hands, but the rules of the game told him it was something ordinary.
It was only later, partly by accident, that he found that if he used a different proportion of nitric oxide, he got a completely different result. His commitment to the standard test, a cornerstone of his normal science, delayed the proper identification of oxygen for years.
That's incredible. Now, a more modern and maybe more dramatic example is the discovery of nuclear fission.
Yeah. In the 1930s, researchers like Enrico Fermi were bombarding uranium, and the paradigm of nuclear physics at the time told them that this might create new, heavier elements from the upper end of the periodic table.
So all their chemical tests were designed to look for things heavier than uranium.
Exactly. They were looking for neptunium, plutonium, things like that. This conceptual commitment made it almost impossible for them to recognize barium, which is a medium weight element, as one of the products. When Hahn and Strassman finally found evidence of barium, they reported it with this intense hesitation. They literally wrote that they couldn't bring themselves to make a leap which would contradict all previous experience of nuclear physics.
Their entire world, the paradigm they lived and worked in, told them barium was impossible in that situation.
The conceptual rules just overrode the data, even when it was staring them in the face. And this failure to see the barium led to almost 5 years of frustrating dead-end investigations. This is why TSK defines discovery not as just seeing something new, but as the recognition of an anomaly. Discovery starts when a scientist realizes that nature has somehow violated the paradigm-induced expectations.
This all sounds deeply psychological, which brings us to that famous experiment with the anomalous playing cards. It really shows how hard it is to see what you aren't prepared for.
It's a really powerful experiment. Subjects were shown playing cards for just a split second, but some of them were anomalies, like a black 4 of hearts or a red 6 of spades. And what happened at first? The subjects just categorized them as normal. They'd say 4 of spades or 4 of hearts. They fit the contradictory data into their existing conceptual boxes without even noticing.
Their brain just auto-corrected reality in real time.
It did. Perception was structured by expectation. It was only after really long exposures that people started to show hesitation, distress, and then finally the sudden disruptive adjustment of their categories. A few people never could see the anomaly.
So recognizing an anomaly is this really difficult disruptive process.
And TSK uses this to show that it forces the scientists to suddenly adjust the very tools they use to make sense of the world.
That sounds unsettling. It makes you wonder how many black 4s of hearts we're missing in our own fields right now.
It's a thought worth contemplating, and if you are enjoying this deep dive into the structure of scientific change, please do take a moment to subscribe and leave a like. Your support really helps us continue to unpack these foundational ideas.
Welcome back. So an anomaly is the first step, but it usually takes more than just one weird result to bring down a whole paradigm. When does an anomaly escalate into a full-blown crisis?
A crisis emerges when that breakdown in normal puzzle solving just persists. It often centers on problems that were supposed to be solved, or when some outside pressure makes the failure especially urgent. The whole field just starts to lose confidence in the existing paradigm.
And a key sign of a crisis is that you get this sudden explosion of competing theories, right? Everyone's trying to patch the system in their own way.
That's exactly it. Look at chemistry before Lavoisier. All these great chemists, Black, Cavendish, Priestley, they were all committed to the phlogiston theory. But they had amassed so much data about different gases that the theory started to get tangled in self-contradictions.
So they didn't want to throw it out,
Right.
but they couldn't make it work consistently.
Right. And by the time Lavoisier came along, TSK says there were almost as many versions of the phlogiston theory as there were pneumatic chemists.
Intellectual gridlock. Everyone knows the system is broken, but no one can agree on how to fix it without just tearing it all down.
And you see the same pattern leading up to Einstein's revolution. Maxwell's theory of electromagnetism was hugely successful, but it depended on this idea of the luminiferous ether, a medium for light waves. For decades, scientists ran all these brilliant experiments trying to detect our motion through this ether.
The famous Michelson-Morley experiment.
The most famous one, yeah. And they all failed uniformly. And the response from normal science, a flurry of patches. Theorists like Lorentz and Fitzgerald proposed these ad hoc ideas that objects contracted in the direction of motion, which is why we couldn't detect the ether. This proliferation of competing, desperate theoretical dodges was a clear sign of crisis.
The framework was just straining at the seam.
It was. And this is a crucial point in the text. The novel theory, the revolutionary one, often emerges only in response to this kind of crisis.
So the ideas might have been around before, but nobody paid attention.
Exactly. Revolutionary ideas are often anticipated during normal science, but they get ignored because the system doesn't need them yet. I mean, think about Copernicus. He was anticipated by Aristarchus way back in the 3rd century BC, who also proposed a sun-centered model. But the idea was ignored because the Ptolemaic Earth-centered system, for all its complexity, worked well enough for the needs of the time.
It wasn't until the Ptolemaic system really started to break down technically. It got monstrously complicated, and it couldn't predict planetary positions accurately enough that the anomaly turned into an acute crisis.
That technical failure, plus external things like the social need for calendar reform, created this urgency. And only then did Copernicus's idea become not just viable, but necessary. Crisis is what prepares the scientific mind for paradigm destruction.
And a scientific revolution is therefore a fundamental transformation.
Mhm.
It's not just a new answer, it's destroying the old conceptual framework, the paradigm, and shifting the methods, the goals, everything.
TSK really emphasizes that the moment of revolution is this sudden, unstructured event. People describe it as a light and flash or a gestalt switch. It's not a step-by-step logical proof. Interpretation only starts after you have this new perception, structured by the new paradigm.
And he has that famous line that the scientist embracing a new paradigm is like a man wearing inverting lenses. He's looking at the same objects, but they're all transformed. This brings us to the most radical and probably most controversial of his ideas, incommensurability.
Incommensurability. It's the idea that successive paradigms are so radically different, they define the world and the rules so differently, that you can't measure them by a common standard. The scientists are literally living in different worlds when they look at the same data.
Okay, that seems impossible. I mean, if I stand next to a scientist from 200 years ago and we both watch a stone fall, surely we both agree the stone fell. Isn't there some neutral reality there?
TSK would say that while the sensory stimulus might come from the same reality, the experience, what the scientist sees as relevant, what's measurable, what even exists, is determined by the paradigm. The classic contrast is Aristotle and Galileo watching that falling stone.
So what did Aristotle's paradigm let him see?
Aristotle saw a stone changing its state. It was striving to get to its natural resting place on the earth. So for him, the important measurements were the total distance covered and the total time it took. That only gives you average speed. He's focused on the distance to the goal.
And Galileo, looking at the exact same event.
Galileo, living in a world that had been conceptually transformed, saw an entirely dynamic process. He was focused on instantaneous speed and the distance fallen from the start. He saw a uniform acceleration, a mathematical law of motion, almost on inspection. Aristotle's paradigm didn't even allow him to ask that question.
So it's not that they're just interpreting the data differently. The framework they learned actually defined what the data was in the first place. They were, in a sense, living in different conceptual worlds.
That's the depth of the claim. And it's not just ancient history. When chemists shifted from the phlogiston theory to Lavoisier's oxygen theory, they came to live in a world where chemical reactions behaved in a completely different way.
And this incommensurability also applies to modern physics.
Yeah.
We often hear that Einstein's theory is just a generalization of Newton's, that it's a smooth progression. TSK argues very strongly against that.
He insists they are fundamentally incompatible. To accept Einstein's relativity, you have to accept that Newton's core concepts, absolute space, absolute time, the conservation of mass, were just plain wrong.
Not just incomplete, wrong.
Wrong. The idea that the old theory is a special case of the new one is something you can only say in hindsight by using the new theory's rules to transform the old one. At their foundations, they disagree on the very fabric of reality.
They disagree on what the universe is even made of.
They do. They differ on the population of the universe. Newton assumes mass is conserved. Einstein says mass and energy are interchangeable. Newton assumes instantaneous action at a distance. Einstein says gravity is the curvature of space-time. These aren't just mathematical tweaks. They're differences in ontology. They disagree about what fundamental things exist.
And because the paradigms redefine the world, they also redefine what counts as a real scientific solution.
That's a huge consequence. The new paradigm judges the old one on its own terms. So when Newton's paradigm took over, it successfully solved huge problems about planetary motion, but it also banished the question of the cause of gravity.
A question that was central to the physics that came before him.
Central. But for Newton's normal science, it became an illegitimate question. It was relegated to philosophy. So the new paradigm redefines what counts as a good problem to solve. Old problems are discarded as non-scientific, while issues that didn't even exist before become the new gold standard of research.
So if these paradigms are truly incommensurable worlds, if there's no neutral standard to compare them, how does a scientific community ever get persuaded to switch? It sounds like it takes more than just logic.
TSK argues that since the paradigms define their own standards of proof, you can't settle the debate with logic or by pointing out an error. The shift is non-cumulative. The transfer of allegiance from one to the other is a kind of persuasion, what he calls a conversion experience.
Which explains why you get these famous older scientists who just resist a new paradigm their whole lives. It's not because they're being stubborn or unscientific.
Not at all. It's a natural consequence of the revolution. Those whose entire productive careers were built on the old paradigm often hold out, convinced that their paradigm will eventually solve its own problems if they just keep working. That resistance is an index of how conservative and powerful normal science really is.
So if proof isn't what settles it, what are the most effective arguments that actually persuade a community to change its world?
There are three main factors. The first, and this is the most compelling one, is problem-solving power. The new paradigm has to solve the major crisis-provoking problems that the old one couldn't.
Like Kepler's tables being way more accurate than Ptolemy's.
Exactly. Kepler's tables, based on Copernicus, just gave much better predictions of where the planets would be. That kind of demonstrable quantitative success is a huge factor. Same thing in the 20th century with quantum theory. The amazing success of Planck's radiation law and the Bohr atom convinced physicists to adopt it, even though it created all these bizarre new conceptual problems.
But problem solving alone isn't always enough, right? I mean, Copernicus's original theory wasn't actually more accurate than Ptolemy's at first.
That's true, which is why the second factor is so potent: unexpected successes. This is when the new theory predicts something completely unsuspected under the old one.
Can you give us an example of that?
Copernicus himself suggested that if the Earth was a planet like the others, then Venus should show phases, just like our moon. This was completely at odds with the Ptolemaic view. And then, 60 years after he died, Galileo points his telescope at Venus and sees the phases. It was this powerful, unexpected confirmation that was really hard to dismiss. Or think about Einstein's general relativity precisely accounting for the long-known weirdness in the orbit of Mercury. An unexpected triumph.
And the third factor is the most subjective one: aesthetic appeal.
These are the arguments that rely less on data and more on an individual's sense of what's appropriate. The new theory is just neater or simpler or more suitable. This appeal to shared values like symmetry or elegance is often what wins people over when the technical arguments are still messy.
It seems like that reliance on values rather than strict rules is a really clever way for the community to distribute risk.
It's the essence of why science works, in TSK's view. Most anomalies get resolved by normal science. Most new theories are wrong. If everyone waited for absolute proof, revolutions would never start. But if nobody jumped early, science would stagnate. So the varied application of these shared values, accuracy, simplicity, consistency, ensures that just enough people take the high-risk step toward a new paradigm while everyone else keeps the old one stable.
Let's pull back for a second and look at the bigger picture for scientific progress. If science moves forward by tearing down its foundations, what does that do to the old idea that science is moving steadily toward some ultimate final truth?
TSK completely dismisses that idea. He says science is not teleological, it's not moving toward a preset goal. He suggests it's much more like an evolutionary process. It's about increasing specialization and accuracy from a primitive starting point, selected by conflict and competition.
So it's Darwin's model applied to ideas. Evolution moves by becoming better adapted from where it was, not by moving towards some ideal future animal.
That's the perfect analogy. And the existence of a shared paradigm is what makes progress during normal science feel so obvious and assured. Because the community doesn't have to constantly re-examine its foundations, it can focus entirely on solving those little puzzles, which guarantees a cumulative result within that paradigm's framework. But when the framework shifts, the direction of progress shifts too.
So if the reality of scientific change is so revolutionary and non-cumulative, why is the illusion of a smooth, straight line of progress so stubborn?
This is what TSK calls the invisibility of revolutions. And it stems mostly from the main way we teach science, the textbook.
The textbook is basically a history book that pretends it isn't one.
It's an aggressively rewritten historical document. Textbooks, he says, focus only on that part of the work of past scientists that can easily be viewed as contributions to the statement and solution of the text's paradigm problems.
That sounds like a pretty powerful institutional distortion.
It's selection by distortion. Past scientists are made to look like they were working on the same problems we are, just with fewer tools. It makes history look smooth and cumulative, and it completely hides the radical breaks.
You mentioned the example of Dalton and chemical proportions. We're taught he was trying to solve that problem from the get-go.
Yes, textbooks frame his work as if he was aiming for the law of combining proportions. But historically, that problem only really occurred to him after most of his creative work was already done. By rewriting the history, the textbook hides the fact that Dalton's original paradigm and the problems he cared about were fundamentally different from ours.
And Newton did the same thing to Galileo, right?
He did. Newton wrote that Galileo had discovered that gravity produces a motion proportional to the square of the time. But Galileo's own writings barely ever mention forces, let alone a uniform gravitational force. His paradigm didn't let him ask that question. By rewriting history to credit Galileo with an answer to a question his paradigm forbade, Newton completely obscured the revolutionary change that had happened between them.
So science as an institution is kind of committed to forgetting its own past context. Why is that functional for the community?
It serves a powerful purpose. TSK suggests that scientists feel like looking at all the historical detail would just dignify human idiosyncrasy, error, and confusion. Why bother with what our best efforts have allowed us to discard? This constant amnesia lets the community focus like a laser on current problems without getting bogged down in philosophical debates, and that's the key to the speed and power of normal science.
But the downside, as you're pointing out, is that the student is trained to see all past scientists as just us, but not as smart, instead of people living in a completely different conceptual world. And that lack of historical perspective could actually stop them from recognizing the next big alternative when a crisis hits.
That is the risk. The training makes you a brilliant puzzle solver, which is essential. But it often fails to teach you how to be a revolutionary, which requires being able to step outside the rules and see the black four of hearts for what it is.
We've covered science from its chaotic beginnings, through the rigid world of normal puzzle solving, and into these disruptive revolutions. Let's finish up with the role of the community itself, and then the key takeaways from this deep dive.
Right. It's so important to remember that a paradigm governs a group of practitioners, not a subject matter. Scientific knowledge is the common property of a group, bound by a shared education, shared goals, and a shared technical language.
And that shared ecosystem is what allows for this incredible level of consensus. Because they all agree on the rules, judgment is pretty much unanimous.
And that consensus, the ability to maintain strong agreement and solve defined puzzles, is what makes a mature science different from other creative fields. The rigor that comes from the group taking its first principles for granted is what makes scientific progress feel so real, even if that progress is evolutionary and not towards some final truth.
Okay, let's summarize the central statements of TSK's argument for our listeners. Let's do 5 key takeaways.
Sounds good. First, normal science is rigid, specialized, puzzle-solving work constrained by a paradigm. Its success actually depends on its refusal to look for fundamental novelty.
Second, scientific revolutions happen when persistent anomalies lead to a full-blown crisis, which forces a destructive and complete shift in the entire conceptual framework.
Third, new and old paradigms are incommensurable. This means their conceptual structures are so different that scientists are literally living in different conceptual worlds when they look at the same data.
Fourth, scientific progress is best understood as an evolutionary process. It's an increase in specialization from primitive beginnings, not a cumulative march towards some fixed ultimate goal.
And finally, number 5. The historical story of cumulative progress we all learn from textbooks is an illusion, reinforced by the way scientists constantly rewrite history to match the current dominant paradigm.
So we end with this question of constraint. If our current, highly specialized fields, whether it's climate modeling or fundamental physics or neuroscience, are all defined by these shared paradigms we get from our training, what are we currently unable to see?
We have to ask ourselves, what ingrained rules, what concepts that we now just take for granted, like the stability of certain constants or the very units we use to measure the world, are restricting our vision right now? What new anomalies or crises might be necessary for our own fields to achieve the next great gestalt switch and force us to finally confront the black four of hearts that's hiding in plain sight?
That is a thought worth carrying forward as you engage the scientific world around you. Thank you for joining us for this deep dive into the structure of scientific change.